Давайте еще раз представлю. Это у нас наш коллега из США Алексей Петренко. Он PhD-студент в университете Южной Калифорнии и сейчас на данный момент исследователь NVIDIA. Вот, Алексей, спасибо, что согласился участвовать. Тебе слово.
С удовольствием. Спасибо, что пригласили. Я должен видеть аудиторию. Ага, вижу, participants появились. Все, понял. Тогда я должен пошарить свой экран. Okay. So, let me start the timer. Roman, when you're ready, can we start? I guess we can. So, as I told Roman already, the topic of my talk today is slightly different from what I sort of announced several weeks ago. It is more broad and, oh, this was creepy. Okay. This talk is more broad and it includes the work that was mentioned on like the title slide and also some older work and some newer work. I tried to compile it into a more coherent story of about how to utilize the power of end-to-end reinforcement learning the best possible way. And so some of you who've been here like a year ago, where I gave my previous talk for MIPT or DataFest, you might have seen some of the slides. So I will try to go through the first part of the talk quickly, and then like spend more time on Megaverse. Okay, so what's the general idea behind what I'm working on in the last couple of years? So we have this daunting problem in front of us. We want to build general artificial intelligence sooner or later, one way or another. And it is a very hard problem. Ideally, sooner or later, we want our intelligent agents to act in the real world, to solve tasks for us. And it's just extremely difficult to work on artificial intelligence directly in the real world. So why don't we start from a task that is more simple, that is more achievable? Let's first work on artificial intelligence in simulation. It's reasonable when you start working on something very difficult to start with an easier version of the task before we've sent a person to Mars. I don't know, let's send a person to Moon or to orbit first. Right, and so it makes a lot of sense to first sort of solve a contained version of the task. And you can think about like what are the problems in reinforcement learning research or in AI in general, and come up with like a lot of them that don't require real world agents at all for us to make progress on. Things like reasoning, memory, compositionality of skill, learning to learn, all of these things we can make progress working on solving simulated tasks. And besides that, it's not just useful for research. There's been a lot of recent evidence that reinforcement learning in simulation can be actually useful for real world applications. I just compiled these 3 examples over here. Especially techniques like sim to real allow us now to train neural network-based policies completely in simulation and then transfer them to real world. As you can see on the left, OpenAI did this successfully. My colleagues on the right did this successfully for drones, and there are lots of other areas where this is being applied. This is like a booming little subfield now. One last thing that I want to say in this sort of motivation section of this talk is that speed really matters, not just in reinforcement learning research, in any kind of machine learning research, or I guess research in general. It is of vital importance that your experiment cycle sort of rotates quickly enough that you can you can check your ideas within like a reasonable time span. You can, I mean, it's pretty self-evident. Like if let's say you have a researcher who is a PhD student or like a postdoc somewhere, and he or she wants to work on the project, and like one experiment takes a year, like how many ideas they will be able to evaluate during their time in academia? Like not very many. But if your experiment takes, I don't know, a day, or better, maybe 3 hours, you can try a lot more different things. And then again, reducing computational requirements and increasing speed of experiments allows you to do pretty much the same research work using less hardware, which significantly increases the involvement and the diversity of researchers. And this is what enables progress. Like we need diverse ideas to move forward. It cannot be that only like 1 or 2 labs in the world can make real progress in these tasks, because we're going to get stuck in like one direction. We need everyone to contribute. So this is why it's so important. And I split my talk in sort of 3 parts, not of equal size. I'll be talking about how people approached training of reinforcement learning policies from systems perspective largely. Like this is a relatively under-researched, if you're allowed to say me this, topic. So a lot of people focus on like core algorithms on how to learn, how to parameterize these policies, how to create loss functions, but not a lot of attention is paid to building systems, like how we convert training data from training data to gradients, how do we collect training data in the most efficient possible way, etc. And then the second part of the talk will be about simulation. So how we build systems to generate this experience that our agents learn from. And then so a couple of cool applications of that. So what would be the traditional approach for a reinforcement learning training project? Like, okay, we want to research, we want to do some research on learning, we want to train some policies, some agents to solve some tasks. So the typical setup involves some kind of environment that you run on a computer, which is normally a type of a computer game or a physics engine. So a lot of those are derived from computer games such as Atari, DeepMind Lab, etc. So typically it's something that simulates one agent in one process or thread of on your operating system, and then to effectively utilize this hardware, you spawn a lot of these processes, you generate a lot of these parallel agents running and collecting experience in these environments. And then the training algorithm is typically like very sequential. So you can think of it as split in phases. We have experience collection phase, we have learning phase, we have the phase where we generate action for next step, and this is how we proceed in a cycle. We're sort of doing one thing at a time only. I included these slides because they have these nice timeline diagrams. This illustrates what are the disadvantages of sort of naively implementing these RL training systems. We can call them the synchronous RL approach. The most typical one, the variations of A to C framework, stands for advantage, actor, critic. This is where we sort of have these OS parallelized processes where we generate the observation during the simulation step, and then we generate actions in a batch for the next step, and then we do simulation again. And this happens until we collect some sort of trajectory of a certain length. And this is our mini batch for learning. And here we do some gradient descent, update the parameters of our policy, and we continue on. So as you can see, there are a couple of disadvantages with it. Like if, first of all, there are a lot of gaps. So like a lot of the time, we're just not doing anything with our hardware. It just sits there doing nothing. And then even if we can somehow mitigate that, like let's say our environment doesn't have this problem that our simulation time is so non-uniform. Even in this case, you can notice that we're only doing one thing at a time. So we only can do simulation or inference or backward propagation, but not all of them at the same time. And this is very inefficient because generally we use different resources. In a lot of our projects, we will use different resources for these steps. So during the simulation, we rely mostly on CPU to run these physics engines. During forward pass and back propagation, we use in GPU, but in different capacity, sort of. So if we could somehow overlay these, if we could somehow execute simulation and action generation at the same time, we could be maybe a lot faster. So can we do that? So there are some ideas already existing on how to accelerate these things. So one of them is called Impulse. This is the work from DeepMind. Sort of they also noticed this, and then they introduced like separate processes for action generation and for learning. So here you can see all of the actors generate their own actions and like do continuous simulation and inference. And then there is a separate process that runs in a background. And then while we are collecting the next mini batch, we can train on the previous one. And then this sort of continues in this fashion. So this is already a step in the right direction because experience collection is decoupled from learning, but still we have the same problem during experience collection that we cannot overlay the two. And also because we have these like learners and actors, they're separate processes. The way they implemented it, there is a lot of communication overhead. So we serialize all of our experience into some trajectories and then exchange observations and parameters back and forth, which is very inefficient. So we have to like serialize, deserialize everything all the time. And if you look at these systems long enough, and if you are motivated enough to sort of accelerate your research cycle, you can identify these bottlenecks. So first of all, RL involves three workloads: simulation, inference, and back propagation, as I mentioned. And typically, overall performance of your system depends on the slowest workload. So can you just run your slowest part of your system continuously without interruption? Like, let's say my system is bottlenecked by simulation. Okay, can I guarantee that my system uses, runs simulation all the time without stopping to do something else and then restarting, right? So it cannot be achieved in the standard approach, synchronous way. And then the second bottleneck is these serialization things that happen. So Ray does it, CDRL, which is another library from DeepMind, does it. Catalyst, that we all know and love, does it, and Paulo does it, etc. So this was the work done about a year ago for ICML last year, where we sort of decided to build a system from first principles. Like first time, sort of we asked the question, like, okay, what would be the proper analytical way to approach this and sort of build the ideal system for this type of computational workload. And it turns out the way to do it is to split these computational workloads even further into even like more atomic processes. And so in our system, we have a pool of processes that only do experience collection, a pool of processes that only do inference in batches, and a process or like a process for every policy we train that does the learning. And one of the key factors that allow the speed up here is the fact that we never actually serialize anything. Like this entire thing operates on shared memory buffers where we put all of the trajectories in the memory that's shared between all of them. And so whenever we have some new information, like let's say new trajectory for the learner to process, the only thing that we need to like signal and send around are some like memory addresses, like, okay, like here you can find a trajectory or two, etc. And so like the entire system becomes very efficient with very little overhead. But it's still not clear like how we're going to mitigate this fact that we have these gaps and this like experience collection cannot be overlaid with inference. So we came up with this idea called double buffered sampling. This is sort of borrowed from the computer graphics in a typical, if anyone programmed a game ever from like first principles, how do you do like smooth update of the screen and fast reaction to user input? You usually have two buffers, and while you render in the first buffer, you show your user the buffer from the previous frame. And then when you're done rendering, you swap them. This is like the most typical approach in all the graphics applications. And we decided to use it in RL as well. So on the top, this would be like your typical implementation where you do a simulation step and then inference step to generate actions. And then you have actions to do the next step of the simulation. But instead, you can split the number of environments that you simulate. Let's say you have, I don't know, like 10 environments. And then you simulate the first 5. You have your observations for the first 5 environments. Based on those, you generate actions. And then by the time you are done simulating the second 5 environments, so environments from 6 to 10, you have actions to start simulating the first half of environments again. And then you keep swapping between back and forth between them like this. So as you can see, the blue line here is uninterrupted. And essentially, like the orange line here is uninterrupted as well. Like if it were the other way around, if the inference workload were more demanding than the simulation workload, then again we would be very efficient here. And so, like what this allows us to do is to like massively outperform more traditional systems. This plot actually doesn't do it justice, because here we compare to other like very fast systems where people already cared for performance and optimized for performance, especially this other work with similar ideas, RLPython from Berkeley. But as you can see, like the difference is still massive. And Impala that I mentioned, that again was designed as like scalable, fast training system, it's like way down there. So we especially noticeable in environments such as like Atari or Doom, where you have a lot of samples coming, and so these performance considerations become really important. You can see like Impala is like way down there, and on the same hardware we can be like, I don't know, 10 times faster than a traditional system. And a synchronous A to C kind of implementation would be like all the way over there. You can imagine what this means in real world. Like if you have an experiment that took you 5 days, and then you use a different system like this, you can complete your training, you can do your research in like a few hours and start testing a new idea. And then again, and then again. And then by the time your colleague trains one experiment, you trained 10 and it got much more insight into your problem. I like to keep this slide that asks the question, how fast actually is it? Like what does these numbers actually mean? Like you have these 140,000 frames per second on a typical system that is like popular in deep learning labs. This is like a small server with 4 GPUs that sort of fits under the desk, not something crazy. 140,000 frames per second in Vizdoom. So it's a 3D pixel-based environment with images where agents run around and solve tasks, right? So at 140,000 frames per second, we collect about an hour of experience per second, about 11 billion samples per day. So you can train your agents on 11 billion samples every day, or 10 years of simulated experience. Or if you train for a week, you can simulate 71 years of experience. And if you read all these papers from OpenAI or DeepMind where they train their StarCraft agents for like hundreds of years of simulated experience, like you can do it. You can do it on a single computer. yourself. And this is pretty cool. I know I showed these slides like more than once significantly, but I really love this. And essentially what it allows you to do is to train some ridiculously optimized policies. Like here, without much effort with a system like this on a regular PC sort of, we attempted these benchmarks in Doom that were like tried by other researchers before. And these horizontal lines are sort of like the previous baseline from a couple years before that, where people even tried to like add some computer vision components to this training system. So instead of just end-to-end RL, people also ran like a computer vision extracting network for features on top of this that was pre-trained to do segmentation and depth, etc. And then just by running a really fast end-to-end reinforcement learning setup, like look here, like we overtake these agents at like essentially dozens of minutes like into training, maybe less than an hour into training, we already passed that, and then we set like new benchmarks in all of them. And this is pretty cool. Okay, so done with this part. I apologize again if anyone saw this before, but now hopefully moving to a part of the talk that would be new for most people. So far we talked about how to approach training, how to build systems that collect experience and turn this experience into gradients, into knowledge that learn from experience. There is a part of the system that we sort of took for granted. Like we have these black boxes that are usually given to us, right? At least this is how most people think about it. Okay, we have this Atari, we have this DeepMind lab environment, and we can like we can put actions into it, and then agents does something and gets us the observation back. And this is like the only thing we can do. And if you think about it, this is not the most optimal way to approach this. The thing is, all of these simulators, they were built initially as computer games. And computer games are designed for humans to observe high-resolution observations of some simulation process, some graphics simulation at sort of human perception rate, right? So you perceive the world at a certain time scale. It doesn't really make sense to show you more than like 60 hertz of updates. And we prefer high resolution. We like to see the world in details. And at this stage of research, the demands of the simulation workloads for reinforcement learning or other types of AI research, they are vastly different. Like what we really want in research is simulating not just one agent at high resolution, but we want to simulate lots of agents, as many as we can, to generate these huge batches of experience for efficient processing on GPU at as fast of a rate as possible. And resolution doesn't really matter all that much. So we are fine with relatively low resolution images because we don't make the brains of these agents really big anyway. Like we're not there yet. So like the agents perceiving full HD observations would be somewhere in the future, but right now we are more interested in agents that like act intelligently, and the resolution of the input is not that important. So vastly different requirements for these environments. This is my main idea. And okay, I have this brief recap of like what's out there already, because you would say like, okay, but we have so many of these environments already, like surely there is something out there that already should fit this sort of set of requirements. And you would be surprised. So let's take a look at like what's out there, what kind of environments people use, and is there an unfilled niche where we can still improve and help the community. So I call this the RL environment zoo. And the first category is these high fidelity simulators that a lot of people focus on. The argument here being is that, okay, let's just make a simulator that's as freakishly close to the real world as you can have one. And then like possibly, like like the argument goes like this: if you can train something in this simulator, then like surely it will transfer to real world, or at least it will be good evidence that a system like this will work in real world conditions, or at least can, right? So good argument, but these environments are extremely slow, and as you can see, when you train on like billions of time steps, it becomes a huge problem. You need these clusters, you need like very complex infrastructure. It's very expensive, a lot of this carbon footprint, or whichever of these downsides you can focus on, it's really difficult to make progress. And then again, even though it allows you to focus on like research on these perception tasks, extracting features, learning from this very sort of diverse input, a lot of these questions that I mentioned on this earlier slide, like compositionality of skills, continual learning, memory, meta learning, any of that, none of that actually requires high dimensional, super high fidelity input to make progress. We can make progress on these even in environments like Atari, and we were able for a while, and then maybe now we have to move forward to something more complex, but not necessarily as complex as the real world already. So like what would be the intermediate step? So while these environments definitely have their place, maybe they're not the ideal starting point for everyone. And then again, the next type of these environments would be sort of modern computer games adapted for RL research. They have much of the same problems as the previous category. High fidelity, diverse, interesting, but too slow. Then there is these environments that we know some of these bigger companies focused on. Have examples here for StarCraft 2 and what was the other one, Dota. So these were like really cool projects, as we all know. And they have advantages over the previous type of environments in that the agents didn't actually use like high dimensional inputs. When their agents trained, they only had like very low resolution renderings of this world, sort of some structured, very low dimensional representation. And while this is more efficient, this is definitely faster than rendering like ray tracing, light, shadows, etc. These are sort of more like board games. And a lot of researchers care about having environments that are more like real world, not in terms of like resolution and graphics, but in terms of other factors, like it's called virtual embodiment. So this is something that we really want to prioritize. If one day we want to understand how to build systems, how to build agents that sort of act intelligently in the real world, they'll have to deal with all of these issues, like how to be embodied in some object, like be a person essentially. Have these egocentric observations, it's called, which are like partially observable world. Everything is 3D, and you have parallax and perspective and all of that. So none of these board games have any of that, any of these factors. And it's very interesting for many researchers to actually have that. So so these definitely have their place, but they're more like board games. You can think about these as like next step from chess to something more complex, but still like not as complex as real world, or at least complexity goes not in the same direction. So another type of these environments that gained a lot of popularity, precisely for the reasons that I'm advocating in this talk, speed and low memory footprint, and it's easy to work with them, is old games. So a lot of research environments are just straight up old computer game engines that were modified to be more flexible so that you can have some training scenarios in these games. And these are great. Like I love this. I love these things. I love Wisdom. I love some of the other environments that exist. And while they are sort of a step in the right direction, as far as I'm advocating, they're still not ideal for these precise reasons that I already mentioned. Like these are designed usually to simulate one agent at a time, and still like optimize for human perception. So to generate a lot of experience, to simulate a lot of observations, we need a lot of them running in parallel. So we end up using something like OS, operating system level parallelism. And then if we use GPU for rendering, we need to communicate back and forth between these processes, etc. And then none of them are usually designed for multi-agent learning. That is another very curious area of research, and we don't have the right tools now to sort of move forward in this. In particular, Wisdom has some features for multi-agent training that involves running a network setup connectivity between processes, which is like very hard to set up. And DeepMind has their own version of DeepMind Lab that does it, that they never open sourced. So like this is ridiculous. We need better tools. And there are these sort of dedicated RL environments. So we are definitely not the first ones to think about like, okay, what if we create an RL environment from scratch? Like this is the purpose of doing AI research in it. So while this is like pretty cool that people do this, it's also surprising that no one had done it right yet. And I'll show like what I mean by that. So there are some environments like this hide and seek environment from OpenAI that sort of has all of the right qualities. Like it has physics simulation, it's interesting, it has virtual embodiment in a way, but the agent here didn't actually perceive the world like we see it from sort of like pixel view, like renderings of the world. They had this low dimensional sort of radar way of looking around them, and sort of flat. And instead of seeing an image, agents see like a line of pixels essentially that describes the world for them. This is not exactly what we are talking about here. This is not really virtual embodiment. And then there are some that did virtual embodiment, like this Unity obstacle tower, animal AI kind of things. But they, again, Unity, if you ever worked with it, is like whatever, like 1000 FPS at most. There's Habitat, which I'll mention later on, which is also very slow. It's not in its natural form, but maybe it can be made faster. So yeah, there is this, seems like there is this unfilled niche to build something. Let's say build something like maybe this hide and seek environments, maybe something like some of these other environments, but do it the right way so we can like actually push the limits of what's possible with learning algorithms. I think I already mentioned all of this. Like, yeah, just to highlight once again, video games optimized for different things than we need for AI research. So this is what we came up with. This thing is called Megaverse. Very ambitious name, but it will be very clear later on why it's called that. And this is a sort of a little computer game that we built from like 0 lines of code. Like, let's say you start with a blank page and you ask yourself a question like, what is going to happen if we decide to optimize and to create an optimized simulation engine specifically for these tasks for RL research? It's like, what are the main considerations? The main considerations are is we want to be really, really fast and keep the environments sort of interesting. Like, what's the right compromise to strike here? So, okay, I'll talk about this, but sort of this a brief intro, like what it actually is. Essentially, Megaverse is like a game engine, but not quite. It's a simulation engine. It doesn't act as a game engine in one specific way that will become important. So the way it's written, it's all in C++ and OpenGL and Vulkan. So it's not something that's like in Python or any of these interpretable languages, because they're just way too slow for the task. So the main the core of the environment is written in all in C++, including the sort of physics and environment and the logic of this little game world. But we obviously provide a Python API to access observations and everything. And as I said, every aspect of this engine is designed for maximum performance. So we go as far as like not only to optimize the simulation like rendering, but also even the tasks themselves, we sort of notice what are the other potential bottlenecks. Like, let's say we want to have physical manipulation of objects. We want agents to be able to pick something and carry the objects around and place them somewhere. And this will require like very fine-grained physics simulation. But here we sort of discretize the physical world such that these objects can be picked up and moved around anywhere, but then you can also only place them on this like discrete grid. And this allows to eliminate the majority of the collision checking and physics calculations from the engine, which allows it to be, for the physics simulation to be like extremely fast. And then this thing is designed with multi-agent simulation in mind. So multi-agent simulation is not the second-class citizen, it is the first-class citizen. We decided to build in this capability like from the very beginning. And one of the main ideas that allows this thing to perform so fast is this observation. I didn't come up with this, by the way. This is based on some ideas from graphics people from Stanford. But essentially, modern GPUs have this capability to render huge resolution textures or images in parallel. So they have a lot of these compute cores. And let's say we have gaming in 8K now, right? So the modern games on modern GPUs can run in 8K in 60 FPS, right? So what does it mean? It means that we can render like a texture or an image that has this many pixels. And like, what if we ask ourselves the question, like, what if we need to render, like, instead of one huge image, we need to render lots of tiny images? So apparently there is a way to do it through particularly the Vulkan API, where we can essentially split this texture into tons and tons of these smaller observations and sort of render a massive amount of different viewpoints in a single render pass. Like you would normally render a single frame, we render thousands of frames at the same time. These can be viewpoints of different agents in the same environment, or these can be viewpoints of agents put in separate training environments. So let's say it could be 3,000 environments. It can be fewer environments with several agents in each one of them. Yeah, and this is sort of the illustration on the right, like how approximately it looks like. So this is sort of the architecture of the system. So in the context of the training system, since I mentioned training systems before, the Megaverse is the simulator here. So like usually we ran the massive number of these process instances that would run a computer game like Atari or Wisdom or something like this. Here we have a different setup. We have very few of these processes actually. Even I would go as far as to say we can have only one Megaverse process in our training system. This process would include a thread pool that simulates like physics of this world on the CPU, and then generate like some states, so like updated positions of objects and cameras and everything. And then we have this entity called batched rendering that sort of sends all of these update commands to the GPU, and you render all of these new observations for the agents at the next time step at once. So like here, you end up with a tensor that contains like 1,000 observations. And then you give it to the inference worker. It is very happy to receive this huge batch of observations and generate actions from all of them at once, again, for efficiency and large batches, accelerating everything. It sends rollouts to the learner sometimes, and then the actions are available to do the next step of the simulation. This can be a part of this asynchronous system that I mentioned before, where we do back and forth swapping with double buffered rendering. But what we wanted to highlight here is that this can be plugged into any training system. Even if you have this like standard A to C style training system, you can massively benefit from having a simulator like this because of this thing, mostly. the fact that you generate like a huge number of these observations at the same time, which is what you want. And this is the exciting slide because it shows, I like when I started working on this, I could not imagine that you can gain so much from this. Like we expected that we would have something like a 10x speed up on some of these like more complex environments. But like this is the final numbers. This is pure simulation throughput, this column over here. So like on a workstation with one GPU, you can simulate 300,000 frames, 300,000 observations per second, which is like you can see the speed up compared to these other environments. So 16 times faster than Atari. And Atari is a flat like arcade game. And here we have actual 3D world with shading and like graphics and virtual embodiment. And like on a bigger system, the difference is even larger. And we were able to simulate 1 million frames per second on a single 8 GPU node, like a relatively typical server that you can find in a lot of clusters or deep learning laboratories. So yeah, and even this even translates to training throughput. So essentially, it is kind of weird how these numbers are entirely bottlenecked by like everything else you have in the training system. So this kind of approach to building simulators, they are so fast that you made sample collection essentially free. And so these things like 100,000 frames per second, these are like entirely bottlenecked by things like backpropagation, how fast you can do backpropagation, calculate gradient on the GPU, right? So one thing to notice, because people might ask, that these numbers are lower than in the previous slides for sample factory. Perhaps I should update them, but this is calculated without frame skip. So this is how many actual observations per second we generate. Because Atari, like all the people usually run 4 frame skip. You generate 4 frames, and then every fourth is observed by the agent. So yeah, especially like essentially you need to multiply this by 4 to get the numbers from the previous slides. But here since Megaverse doesn't use frame skip, like the agents, it is already designed to run at a certain like desired frame rate for the RL setup. We don't need frame skip, and so we need to directly compare like how quickly we collect experience, and it is pretty obvious like how much faster this is. I can say a few words about this, some of the other optimization ideas that we came up with. So we found it really efficient to build this sort of discretized Minecraft-like worlds, because they still allow some very interesting behaviors to emerge, or some very interesting research to be conducted. But if you naively implement them, you will not be able to squeeze a lot of performance from it, because any sort of larger 3D geometry of the level of the environment will require a lot of polygons and a lot of physics calculations. So one of the things that we are doing here is coalescing these voxels via some sort of like traditional algorithm into this like bigger structures. Sort of before we like when we procedurally generate these levels, we minimize in a certain way the amount of geometry. I mean, this is a pretty obvious thing to do, but this really helps. And then again, as I said, the physics part of the calculation, like when agents, like how the agents should move with respect to the actions, etc. This is this engine is designed to run at like sort of the right frame rate from the beginning, such that we don't have to introduce things like frame skip, and so we don't ever waste computation on like generating frames that we won't actually use. And there are some other things. So I think this is like one of the examples of how this is one of the environments that is available in Megaverse. So there are these obstacle courses, for example, And this is how the agent would interact with the objects in the environment. And as you can see, like here, you have to do a pretty lengthy process to build this sort of ladder and climb it and pass this obstacle. So this is just an example of how one of the environments that can be created with this engine can look like. And so the way this is available to the training system is very, very similar to how a standard gym interface looks like. So we have these actions, we have these observations. The only difference is that like everything is vectorized. So instead of having one action and one agent, you have lots of actions and lots of agents. But this is actually like very simple usually to use with all types of training systems. One important thing to mention is that we promote this as a general platform. So do not consider this as just like another benchmark, but a general platform where people can build their own tasks, their own single agent, multi-agent environments to do their own research. And there are tools to do this. But to sort of introduce this to the community and promote this, we built a set of environments ourselves. And we called this benchmark a Megaverse 8. This is 8 different environments built on this engine. They are all as fast as the numbers suggest from previous slides. I mean, not equally, but in the same ballpark. And they are designed to sort of be a comprehensive benchmark of that is relevant at the modern stage of development in RL training, right? So we have all of these issues that are sort of remain unresolved: exploration, memory, how to train agents that can manipulate object or plan over the long horizon, etc. And different environments from this benchmark, they sort of emphasize different of these challenges. And some of them are made a little bit easier, some are much harder. So what we of course attempted is to try to train like a state-of-the-art RL algorithm on this. And coming from someone who'd done a lot of RL, we sort of put sufficient effort to go ahead and optimize this. Actually, can I just? And so what we found is that with the best tools we have, like training with a very fast and efficient learning algorithm, we can achieve progress on 4 of these tasks. And on other 4, the agent achieves pretty much 0 progress. And we were sort of very happy with this, because this suggests that the benchmark in sort of the right place. First of all, none of the environments are fully solved. So none of them approach like the 1.0 fraction of success. And then some of the environments, the agent doesn't even make progress at all, which sort of introduces the challenge. Like, okay, now the researchers have environments that are really, really fast and easy to work with and don't require a big cluster to make progress on research. But you have completely 0 training on some of these tasks and like subpar training on some others. Like, okay, what can we do? What kind of ideas can we test? Because now you don't have the excuse that you didn't have enough samples to train them. We show that you can train even to 10 billion samples on this environment, and you still don't have any, don't achieve any progress. Like, so it's not constrained, it's not limited, but by the amount of experience we can collect. So we need better ideas, and this is what it's all about. Like, we want to create tools, we want to create setup where lots of researchers can experiment and introduce new learning algorithms, new ideas into this. So hopefully we can make progress in sort of general learning ability of our AI. We also trained some multiple agent policies with also some pretty interesting results. I recommend you read the paper if you want to know the details. Since I'm running out of time, I'll show some of the cooler policies that we trained with this, and this is perhaps my favorite. So this video shows the agent that is performing the task. So this is not human plane, this is the neural network policy trained in this environment, executing the task. So here, like one of the environments from Megaverse 8 is called the tower building. And the task is very simple. You have this rather large amount of these interactable objects, cubes available to you. And the task is to build the tower that is as tall as possible. And so you are rewarded for placing a cube in this black building zone as high as you can. And so from this very simple reward signal, we were surprised to discover that the agents learn these like very complex behaviors. They run around in these environments, and the episodes last like 10,000 steps, and then they just keep building, and they have this sort of developed this sort of strategy to build this scaffolding around like a central part of their building that they are creating, and they keep carrying the cubes all the way. And this reminds me sort of like what ants or some other insects are doing, where they build these amazing structures. So yeah, again, the exciting thing for me here is that this is sort of like state of the art in embodied AI in RL. There's a pretty cool kind of policy or behavior. And at the same time, you can train it on a laptop. And I'm not exaggerating. I was on a trip when I was creating creating this part of this work, and I had a laptop with me, and I trained some of the policies on a laptop in a hotel room when I was experimenting. If you can show me some other environment that can allow this, I would be excited to learn about it. And this continuation on the same task, this is like another interesting result that we found, is that apparently if you give agent, so in the training distribution of levels for these agents, we had like limited size of this environment, and the number of blocks was never larger than is required to build like a 10 level tower. So I think there were like 55 blocks or something in the environment at most. And so we would think that the agents would stop there. So like usually these policies do not generalize beyond the training distribution. But here we actually found that if you give it a lot more of this training building materials, then it can just like keep building. And we saw agents building these towers up to like 15 levels higher, which again, like as you can imagine, requires like way more blocks and even longer horizon planning sort of thing. So what it suggests is it sort of has this general ability now to build the structures, which is pretty exciting. So this video like goes on a while, and as you can see, this is kind of the construction that this agent directs. Yeah, this was pretty interesting to find. And there is a website dedicated to this project. If you go to this website, you can find some more of these videos and performance in some other environments, and sort of like descriptions of other environments in Megaverse 8, etc. And I recommend, if you are interested, go check it out. All right, so very much the final part of the talk. I covered like important things that I wanted to talk about. A couple of words on like where else this can be applied, these ideas. So this work is relatively new, and I didn't have a chance to spread much yet, and we are hopeful that sort of more researchers will pick up on this. But there are a couple of projects already that were inspired by this sort of ideas of making environments much faster and experience collection cheaper, etc. And sort of like one of the things was this project. This was done by a master student here at USC, and again using all of these similar tools from the first part of the talk that I mentioned. So Again, like the key to a lot of this research project is having the tools, having the infrastructure to run a lot of experiments and to have this fast simulator. And we were interested in the question like how the agents can learn from different modalities of input. Like let's say we don't just have the visual input like a rendered frame, but also let's say we have sound, and all of these computer games have sounds in them. So like can we learn something from the sound? Can we build an agent that, let's say, plays the game better, having access to in-game sounds? And again, we found that there are just no simulators that allow you to do this in any sort of meaningful, like fast enough way, because sound subsystems are usually tied to like a sound rendering device of some sort, again, adjusted for human perception. So if you want to do large-scale training of very complex policies, you are out of luck. So we built this version of Wisdom that has a completely different sound pipeline, which is based on like software sound rendering, and allows you to run in the same sort of frame rates of 100,000 frames per second. But you have a game with vision and sound. And we found that with a good enough policy architecture, you can have like pretty interesting policies in them. So again, there is a website, you can check it out. There are some videos that demonstrate the performance of these agents. I'm not sure if I can actually like share the sounds from my computer, because these of course require yeah, I don't know how to do it. So like, okay, I'll just explain. So in these environments, for example, you have the voice instruction of like what objects to go to, and the agent learned to listen to this voice instructions in plain English, and then go approach a specific object. And we have environments like this. And eventually we even trained like a full agent for a computer game, like a 1v1 deathmatch, where one agent plays against another. One agent has access to sound and another doesn't. And we found that the agent that can listen to in-game sounds can perform better. So this was one interesting project in this sort of area. Another thing that I wanted to mention is Habitat, that we skipped over very quickly at the very beginning of the talk. So this was done sort of in parallel with the Megaverse work, slightly earlier. And here we applied the same ideas of batched simulation and rendering to something that already existed, right? Rather than building the environment from scratch, we took Habitat and we optimized it in this way. So instead of rendering like one scene at a time, we sort of do this like batches of observations. And then again, you can see what kind of performance speed up we can squeeze out of it. So this work is available. It's called Large Batch Simulation for Deep Reinforcement Learning. So if anyone's interested in Habitat training, you can check it out. So you can compare the numbers that like this work, Wyman's from 2020 was state of the art on Habitat. There was a challenge and they won it. And this is sort of the performance figures that they had in their training system. So yeah, this is like hundreds of frames per second on a single GPU. Yeah, and so as you can see, like we bumped it to like it became ridiculously faster. So from hundreds to tens of thousands of frames per second using similar ideas and some other optimizations. So check out the work if you're interested. And the final thing I'll say is like where this is going, like what's the way forward, like what's not done yet. As you can see, the end-to-end simulation and learning is very powerful and allows you to do a lot of cool research and potentially even do some real world applications with techniques like domain randomization and sim to real transfer. So another like parallel direction, people from NVIDIA developed this thing called Isaac Gym, and this is a physics simulator on the GPU. So again, similar idea, but as I mentioned before, we do our like little physics calculations in Megaverse on the CPU, and they are fast because the worlds are relatively simple. But with Isaac Gym, you can actually do very complex physics manipulation, including contact and forces and everything on the GPU, and much faster. And then again, you can simulate a lot of these agents in parallel, which is very good for batching, and so everything's faster. And one thing that had been done yet is the efficient combination of the two. So like, can we have very fast physics and rendering at the same time? So this is maybe something to think for the future. Yeah, that's all for me. I think it's exactly an hour. And if anyone has any questions, please let me know.
Yes, thank you, Alexei. It was really very interesting talk, because we actually had some issues with some environments, and I guess Alexei Staroverov maybe have some questions about habitat. Actually, yes. So I allow him to talk.
Да, мне только мне это по-русски или по-английски?
Давайте
Или
по-русски.
можно? Да. Спасибо. Вот у меня такой есть один. Сейчас, секунду. Можно спросить, вот по сути такой end-to-end RL, то есть он может хорошо справиться в каких-то тасках, но иногда, то есть вот если взять тот же Habitat, то в Point Nav треке, то есть если взять условие, что у нас у агента есть GPS координаты, то вот в такой в постановке end-to-end, там вот, по-моему, была статья, то получается нужно где-то 100 миллионов кадров, а вот если убрать этот сенсор, то уже даже пробовали обучать, по-моему, где-то 2,5 миллиарда шагов. И
я очень хорошо знаю, о чем ты говоришь.
Да. И вот получается, вот был Point Nav трек и в прошлом году, и в этом году. И вот как бы стоит ли все пытаться делать end-to-end, или все-таки можно как бы использовать какие-то как бы дополнительные как бы структуры. Ну, то есть вот даже в том же Point Nav треке те, кто заняли первое место, они, то есть, брали сетку, которая, по сути, как бы получает вот эти вот координаты, по сути, из тех же observation'ов, и вот как бы получается, что такой end-to-end RL, ему самому это восстановить было очень сложно. Ну, то есть,
да, Алексей, я понял вопрос. Давай я прокомментирую сразу несколько вещей, которые ты сказал.
Да.
Значит, во-первых, я не зря привел, точнее, мы не зря цитировали именно вот эти работы в Large Barge Simulation статье. Wyman's 20 — это как раз победитель, мне кажется, 2019 года, то есть соревнование было в 2019 году, в 2020 была статья. И это как раз та работа, про которую ты говоришь, где тренировали на 2,5 миллиардах сэмплов или что-то такое. Ridiculous. Да. Вот, я работал с этим человеком, с Эриком. Мы вместе в прошлом году были летом в Intel с Владленом Колтоном, и как раз он был частью вот этой работы по оптимизации и Megaverse, и Habitat. Значит, как они этого достигли? Во-первых, наверняка ты, Алексей, знаешь, но для тех, кто не занимался этим, они работали с Фейсбуком, и у них был кластер, по-моему, у них было 64 сервера по там 8 GPU в каждом. То есть ты представляешь, сколько это мощности. Это если арендовать такое на там, AWS, это миллионы долларов. То есть они потратили эквивалент миллионов долларов на тренировку этой модели. Это, не, скажем прямо, доступно не всем. Вот. И что мы выяснили, то есть после этих оптимизаций, после того, как мы еще сжали модели, после того, как мы оптимизировали с помощью батч-рендеринга сам подход к симуляции, мы смогли натренировать практически такой же перформанс с точностью до, по-моему, 0,3% или что-то такое на point-nav навигации на одной машине за, по-моему, 3 дня. То есть вот та фигня, которая была у Эрика, она тренировалась там неделю на 64 8 GPU-шных огромных серверах, мы оттренировали это на одном сервере за 3 дня. Да, такой же перформанс. То есть это к вопросу о том, что даже в таких реалистичных симуляторах, как Habitat, если правильно подойти к вопросу оптимизации и тренировки, даже end-to-end learning можно заставить работать в таких реалистичных условиях, то есть без доступа к гигантским кластерам. Это к вопросу о том, является ли end-to-end RL вообще feasible. И я повторюсь, Wymans, они выиграли, то есть были другие участники, которые придумывали другие подходы, что-то притренить, какие-то фичи, что-то более умное, и простой end-to-end learning, простой PPO выиграл, насколько я понимаю, в тот год они, по-моему, они выиграли.
Да, но вот если брать это вот, сейчас, извини, вот если брать самый первый трек вот в 2019 году, то да, то есть вот такой end-to-end стал первым, но вот потом, получается, в текущем они уже как бы взяли чуть-чуть более сложную таску и уже вот такой end-to-end подход, да, то есть он как бы ушел немножко вниз, и вот они даже писали в статье, что вот в более сложных условиях они, то есть брали даже вот там сколько-то уже и степов гораздо больше, и вот такой end-to-end у них все равно очень сложно было его, по сути, сделать.
Понял.
А вот...
Значит, смотри, тут я как бы сказал первую вещь, которую я хотел сказать, теперь вторая вещь. Я ни в коем случае не адвокат того, что мы должны остановиться на end-to-end learning с помощью там, самых простых идей, да, полиси градиента и все, и пошли домой, пока все тренируется. Конечно же, нужно придумывать какие-то более мощные, общие, интересные идеи, которые позволяют более эффективно тренироваться, более быстро учиться и так далее. Идея в том, что какая бы идея не пришла в голову ресерчеру, какую бы идею не хотел протестировать, вопросы перформанса, они никуда не уходят. То есть если тебе нужно собрать не миллиард, а 100 миллионов сэмплов, тебе все равно нужно собрать 100 миллионов сэмплов и как-то натренироваться на них. Поэтому вопрос вот систем для тренировки, он никуда не уходит. И поэтому я считаю, что вот эта область, ну как бы такая наша маленькая область исследований, которой мы занимались, вот эти системы, она является важной, потому что она влияет на все остальное, как бы на все даунстрим задачи. И если ты применишь эти идеи, то они тебе помогут там тоже.
Да,
понимаешь,
хорошо, спасибо. Да, а вот...
Единственное, я не могу прокомментировать конкретные подходы, которые там применяли люди, наверное, в том соревновании, потому что я сам в нем не участвовал, я не так много про это знаю. Но задавай вопросы, если я постараюсь ответить.
Да, а вот у вас вот, по сути, с этим хэбитатом есть какие-то более дальше планы? Ну, то есть вот я вот просто пробовал брать этот симулятор, и то есть он в целом очень как бы быстро все отрабатывает, но вот его если его сравнивать с оригинальным, то там очень есть много функций, которых, по сути, нету. Ну, то есть, или там нужно очень много самому все вручную прописывать или какие-то новые функции.
Ты имеешь в виду, ты брал
Да.
симулятор, который из вот этой работы, то есть уже оптимизированный?
Да. Он, по-моему,
Ага. Да, но здесь надо понимать,
BPS,
что... Да. Здесь надо понимать, что это было по большей части как бы proof of concept работы, то есть это не было частью как бы общего эфорта по разработке Habitat. Этим занимается там своя команда в Фейсбуке, и мы не были с ней ассоциированы вообще. То есть это была работа, которая призвана показать, что типа вот как надо делать. И мотивировать людей в будущем делать симуляторы и системы для тренировки, которые как бы не выбрасывают, как сказать, waste, вычисления и hardware и так далее. Насколько я знаю, то есть люди, с которыми я работал, некоторые из них сейчас являются частью команды Habitat, то есть с большой вероятностью какие-то из этих идей будут добавлены как бы в официальный репозиторий, в официальный API. И вот я знаю, что недавно вышел Habitat 2.0.
Да.
Но, да, то есть, да, ну вот, значит...
Ну, у них он, по-моему, даже еще более медленно работает, там они полностью и физику переписали. То есть у них там теперь какие-то вот эти вот, можно как-то интерактивно взаимодействовать со средой. То есть они уже, мне кажется, ушли на немножко другой класс задач.
Давай я тебе предложу следующее. Поскольку я с тех пор, как мы закончили ту работу с Habitat, не взаимодействовал особенно, я не знаю точно, в каком состоянии все это находится. Вот я вижу, здесь они написали цифры, что до 26 тысяч simulations per second, steps per second. Ну, это типа сильно быстрее, чем был раньше Habitat. Это что-то типа in the ballpark of то, что было в нашей статье. Если ты говоришь, что это тебе недоступно, таких цифр нет на самом деле, я могу связать тебя с людьми, ну, то есть конкретно с Бреннаном и с Эриком, и ты можешь, наверное, им эти вопросы задать или через меня как-то релей. Если ты напишешь письмо, я могу поставить Эрика Брайнана в копию, и они могут тебе подсказать, что, может быть, тебе нужно сделать. Okay?
Да, хорошо, спасибо. Я вот, по-моему, с Бреннаном немножко в Slack общался, то есть там просто даже были какие-то такие ошибки, ну, там что-то с конфликтом, какие-то версии. Там у меня плохо, плохо ставился, да. И вот Брэннон, да, там он немножко помог. Так что, да, я тогда еще более четко сформулирую, и тогда тебе
ставь меня в копию,
напишу.
У тебя будет лучше шансов получить ответ, если я пингану. Да, значит, одну вещь, которую нужно понимать про, ну, такие вещи, как BPS, например, то есть вот эту штуку. То есть это, естественно, основано на самых cutting-edge технологиях из там компьютерной графики, там Vulkan API, определенной версии, определенной версии NVIDIA-ских драйверов нужна и так далее. То есть это, наверное, ожидаемо, потому что если бы это было доступно 10 лет назад, люди бы уже так делали. То есть есть что-то такое в том, чтобы быть первопроходцем в таких вещах. Да, немножко приходится сталкиваться с тем, что где-то там на самой стандартной Ubuntu что-то где-то не поставится, но эти задачи очень решаемые. У нас уже много кто использует и Megaverse, и BPS, и люди ставили это на разные кластеры, и в докер, и так далее. И мы там стараемся писать инструкции в GitHub, как это делать, как траблшутить разные задачи. То есть не ожидайте, что это будет прям так же легко, как там pip install Atari, но типа это не намного сложнее. Типа какой-нибудь там час потратить на решение одной-двух проблем, или если что-то более сложное написать, GitHub issue создать, и, скорее всего, ваша проблема решится. Ничего такого в этом нет.
Да, но вот в результате в докер, да, получилось все нормально поставить. Да. Так что вот я сейчас тоже пробую все свои алгоритмы в нем
Отлично.
тестить. Да, спасибо большое.
Алексей, спасибо за классный рассказ. Вот, я видел твое, наверное, прошлогоднее или позапрошлогоднее видео тоже вот как раз в нашей лабе, то, что ты докладывал по Виздуму. Вот, я вижу, то есть еще теперь добавил еще Megaverse. Правильно?
Много чего добавил, да, но здесь в этой line of work, да, вот они в одном месте где-то оказались.
Я, честно скажу, я просто подключился немножко позже с твоего начала, поэтому смотрел тебя практически на X2, вот, и мог некоторые моменты слегка, ну, то есть пропустить, если что, говори просто, что это было, я пересмотрю. Я не очень понял про Sample Factory, собственно, как этим можно пользоваться, если ты там не берешь не PPO, а какой-то свой, там, разрабатываешь свою модель, свой алгоритм, какой-то свой метод. То есть у него какой-то API есть или что? Просто я вот сейчас смотрел в GitHub, там просто через командную строку запускается что-то уже как будто бы готовое.
Да, хороший вопрос. Значит, это такой проект, то есть задача не стояла создать еще один RL-фреймворк, хотя это в какой-то степени получилось. Задача, когда мы работали над этим изначально, была тоже сделать такой proof of concept, что типа, окей, если сесть и подумать над архитектурой, над тем, как правильно сделать communication между компонентами системы и так далее, то можно сделать систему, которая в 10 раз быстрее обычной, да? То есть здесь нет ничего такого специфического в алгоритме PPO, что эти идеи не распространяются ни на что другое. Ты можешь применить эти идеи к любому другому алгоритму. Дальше конкретно по той кодовой базе, которая есть, мы не стали имплементировать много типа других алгоритмов. Есть и так миллион фреймворков уже, и
ну, да.
Но типа сделать это несложно. Значит, во-первых, что можно сказать? 90% алгоритмов, которые policy gradient, они так или иначе являются вариациями на тот же actor-critic. То есть они не отличаются от там стандартного алгоритма с точки зрения систем. Они отличаются, какой-нибудь у тебя будет другой loss function, какая-нибудь другая модель, там entropy reward и так далее, да, то есть все вот эти вещи,
верно.
Их можно добавлять как модули, там в Sample Factory полно этих модулей есть там всякая энтропия, Kyle Divergence, там есть V-Trace из Impala, там есть CPC, это Contractive Predictive Coding, и еще, ну, такие модули, то есть их добавлять легко. Если нужно сделать алгоритм, который вообще отличается архитектурно, например, off-policy алгоритм, скажем, ну, что-то типа вариации Q-learning какого-то, то, да, нужно, в Sample Factory нет, но можно брать те же принципы или даже те же компоненты и сделать такой алгоритм будет достаточно легко. Плюс, если ты хочешь что-то off-the-shelf, я рекомендую попробовать вот такой фреймворк. То есть это ребята из Беркли, которые делали похожую работу по оптимизации примерно параллельно с нами. У них не такие впечатляющие цифры получились в плане там, максимального перформанса, но они больше внимания уделили тому, чтобы прям сделать фреймворк из этого. И здесь есть всякие разные R2D2, Q-learning и так далее. То есть тоже быстро, хотя не так быстро, но типа более гибко, более как фреймворк. Это как оправдание прозвучит, но я как бы отдаю себе отчет в том, что у меня нет большой команды, у них там в Беркли было, ну, несколько людей сотрудничали. Я не хочу весь свой PhD заниматься разработкой фреймворков и писать, ну, software development заниматься. Это и так занимает огромное количество времени. Так что это компромисс. Я бы с удовольствием превратил Sample Factory в фреймворк, который бы все ресерчеры использовали, но приходится делать компромиссы.
Не, супер. Наоборот, мне кажется, даже это может быть даже лучше. То есть я правильно понимаю, что в статье, которую вы опубликовали, или там несколько статей, вы как раз, собственно, сами идеи, то есть сами, ну, как бы, короче говоря, принципы, как можно распределить, как можно, то есть как распределить это, то есть эти три шага, там, симуляция, инференс и backpropagation, как можно их распределить, как можно все закодировать. Вы все это описываете, да, и на уровне, то есть советов.
Да, идеи как бы более абстрактные продвигаются. И типа есть reference code base, который показывает, как это может выглядеть в реальном мире, да. То есть это такие кирпичики, которые, по идее, нужны там следующему шагу ресерчеров, следующему поколению ресерчеров, так сказать, чтобы их системы строить. То есть моя главная мотивация была это вот показать людям, типа, окей, заканчивайте там использовать OpenAI baselines и тренировать свой там Муджока Хоппер по 2 недели. Вот как надо, типа, давайте делать системы таким образом. И я вижу, что люди переключаются потихоньку на такие более продвинутые системы. Для того же RL, там есть вот новый репозиторий от DeepMind, да, который называется SeedRL, и какие-то мои коллеги стали его использовать. Какие-то мои коллеги используют Sample Factory, модифицируя ее там тем или иным образом.
Понятно. У меня еще есть куча вопросов, на самом деле. Второй вопрос по Мегаверсу. Можешь рассказать примерно, собственно, как примерно задаются, собственно, свои сценарии? И вообще, как можно взаимодействовать с библиотекой, ну, то есть с этой средой, как разработчик именно сценариев каких-то, там, я не знаю, хочу добавить новые виды, называется, господи, ну, то есть, типа, вот звуки, про звуки говорил, там, не знаю, еще, может быть, запахи можно добавить, там еще что-то, какие-то виды входа. Что-то такое.
Значит, я могу неким общим образом ответить на этот вопрос, наверное.
Ну да, то есть
не только к Megaverse, а к любому подобному research-репозиторию, как бы предусмотреть все возможные сценарии невозможно. И единственное, что я могу сделать, это создать некий костяк и как бы заинспирить людей форкать и экстендить его. То есть по определению research — это такая область, где билдить инструменты для того, чтобы предусмотреть все возможные случаи, это практически невозможно, потому что
это
эти
глупо даже немножко.
новыми. Да, но как бы код open source, и надо понимать, что это написано одним человеком там в течение, не знаю, 3-4 месяцев. То есть кода здесь мало достаточно. Это не какой-то там Unreal Engine, да, который там черт ногу сломит, и ты будешь полжизни в нем разбираться. Это достаточно крохотная такая кодовая база. Написано все это на C++. То есть если ты хочешь создать свой сценарий, я рекомендую просто не пугаться, а пойти посмотреть, как сделаны сценарии, которые есть в игре. Есть там libs scenarios. И каждый сценарий определен просто своим классом. То есть это немножечко C++ кода. Как я уже сказал, мы на самом деле размышляли на этот вопрос, нужен ли как некий питоновский API на более низком уровне, чтобы именно самую логику сценариев писать на питоне. Решили не делать этого, потому что питон очень медленный. И если там SpyBullet с физическим движком взаимодействует через питон, это вообще забей, никакого миллиона там даже близко не получится. Вот. Поэтому, да, все сценарии написаны на C++, но опять же, то есть написать там, ну вот, например, Сокобан, да, вот трехмерная версия Сокобана, которая у нас есть. Ну смотри, 290 строк кода. То есть можно зайти, посмотреть, как сделаны существующие сценарии. То есть есть некий API на C++, который включает разные компоненты, которые, значит, уже используются в других environment. Ну, например, стандартные вещи, вот этот voxel grid для взаимодействия, для как бы spatial queries, посмотреть, что рядом с тобой и так далее. Это уже все есть. То есть такой стандартный подход — это посмотреть самый похожий environment или похожие environment, которые есть, и, значит, взять тоже API и написать свой, или не знаю, спросить меня, если что-то совсем non-trivial. А дальше как бы это Turing Complete Language, пиши, фантазии на что хватает.
Ну да, я, в принципе, это как раз хотел знать. То есть у вас, может быть, конфиги какие-то, которые задают, задают как бы язык задания сценариев, или это действительно кодом? То есть кодом тоже отлично, на самом деле, возможно, даже лучше, потому что выразительность...
Да, полная свобода.
Не ограничен ничем, да, не ограничен ничем.
Лично я такой сноб, я типа чаще люблю написать свой код, чем сидеть исследовать какие-то библиотеки. И тут в этом плане, если ты также любишь работать, то здесь даже, наверное, проще, потому что тебе не нужно исследовать там какую-то документацию неделю. В принципе, там за полдня можно понять все, что тут есть, и просто сесть и написать свой сценарий. Тебе будет так проще.
Слушай, а вот ты говорил про то, что можно много агентов одновременно там как-то просчитывать в среде. Есть ли там что-то связанное с общением агентов между собой? Или это пока тоже не делалось?
Да, очень хороший вопрос. Здесь, наверное, пока нет вот API, который этого поддерживает прямо. То есть это нужно добавлять некие дополнительные там action observation spaces для вот этого общения. Эта тема мне очень интересна. Мы даже в статье, по-моему, упомянули, что типа да, это был бы один из крутых use cases. Причем мы упомянули это и в Megaverse, и в SoundRL. То есть давай научим агентов не только слушать, но и разговаривать. Вот, но да, пока прям конкретных шагов в этом плане нет. Я очень поддержу любой effort, чтобы заэкстендить Megaverse, чтобы в нем можно было такие штуки делать. Я не думаю, что это очень сложно. То есть, опять же, я думаю, что такие вещи можно там за несколько дней сделать.
Супер. И последний вопрос, чтобы тебя уже не задержать, там, может, еще какие-то вопросы есть. Смотри, я просто о чем подумал. Ты вот говоришь про то, что простыми алгоритмами можно, ну, то есть простыми методами, просто увеличив количество сэмплов, по сути, уменьшив стоимость их получения, можно получить очень крутые результаты, и это как-то немножко соотносится там с известным гетеролессом Саттона, да, о том, что, типа, простые системы, они лучше скалируются с вычислениями. Вот. Я подумал, что насчет, собственно, попробовать и какие-то метаметоды, то есть методы метаобучения, собственно, если у нас такое количество огромных сэмплов, какие-нибудь, там, не знаю, генетические алгоритмы там, или просто нормальные метаобучение, какой-то подбор архитектуры и так далее. Вот не думали вы в эту сторону?
Мы с тобой, видимо, очень синхронизировались, мы прям на одной волне. Ты продолжаешь пересказывать, по-моему, conclusion к статье Megaverse. Если я открою, по-моему, там вот эти две идеи ровно высказаны как бы в conclusion and future work с текста и статьи, так что прочитай. Да, у меня как раз были идеи, значит, про meta-learning. Интересно то, что если создать прям маленькие таски в Megaverse, там какие-то, ну, вообще элементарные, да, то есть у тебя целая training session от random policy до решения как бы может занимать какие-то секунды. То есть реально даже не минута, а секунды на полный convergence агента. И когда у тебя такой sample режим, можно думать уже о том, чтобы сделать его частью какой-то более крупной тренинг-системы. И мне очень нравится идея обучаться, да, ну это там Шмидхубер еще, не знаю, там в прошлом тысячелетии придумал, но как бы это реально можно сделать сейчас. И у меня вообще есть такая идея, что reinforcement learning вот в текущем состоянии в 2021 году, он чем-то похож на там computer vision в 90-е. То есть когда мы сидели и там придумывали фичи какие-то, да, там как какой-то прямоугольничек там черно-белый замачить на картинку, провести по картинке, потом там несколько таких собрать, и вот там это лицо на каком-то там бустинге, да. Вот RL чем-то похож на это. У нас все наши алгоритмы, они являются rule-based. То есть есть какое-то очень простое правило или какая-то простая математическая формула, которая пытается описать в целом такое явление, как learning, обучение. И я считаю, что, в принципе, такие вещи, как learning или exploration, они не сводятся к одной простой математической формуле. Это очень сложные процессы, такие же, как зрение не сводится к математической формуле, также и обучение не сводится к математической формуле. Поэтому в идеале, в будущем, когда мы будем делать более продвинутый искусственный интеллект, мы должны иметь инструменты, чтобы обучать как explore и обучать как learn. Вот. Может быть, мы уже можем подступиться к таким задачам, вот используя инструменты такие, как Megaverse.
Слушай, да, мне на самом деле тоже хорошо откликается твоя идея, поэтому мне нравится твой ответ. Окей, я с удовольствием читаю статью. Они были как раз, да? Это статья по Megaverse как раз, да?
Это статья по Megaverse, да, вот здесь. Да, вот здесь мы про мета-learning говорим. То есть статья, ее еще нет на архиве, но она будет там через пару недель, и ее можно найти где-то, по-моему, на сайте Владлена, он ее выложил уже. Если хочешь почитать, на сайте Владлена есть статья.
Хорошо, спасибо.
Там recent publications. Вот.
Так, ну ладно, Алексей, большое спасибо за доклад, мы так уже немножко задержались. Было Было очень интересно. Мне кажется, получилась классная сессия вопросов, и в целом доклад получился очень такой полезный, особенно для тех, кто занимается различными средами и хочет их как-то ускорить или сделать как-то эффективнее. Поэтому еще раз спасибо за доклад. Были рады тебя слышать, видеть. И...
Спасибо, что пригласил еще раз.
Да.
Как всегда, было интересно.
Да.
Готов пообщаться, пишите мне офлайн. Я еще пока не настолько загружен, чтобы там игнорировать. Ну и герои 3, как бы, обязательно.
Да, по героям обязательно договоримся, я тебе обязательно напишу, и пишите вот Алексею по вопросам. Спасибо, все, всем пока.
Пока, хорошего вечера.
Да.